Hello, this video is for the Algebra 1 textbook, lesson 4-3. It's titled Writing Functions, and the objectives for this activity are to identify independent and dependent variables, to write an equation in function notation, and evaluate a function for given input values. The vocabulary words for this lesson are independent variable, dependent variable, function rule, and function notation. So why learn this? Well, you can use a function rule to calculate how much money you will earn for working specific amounts of time. So let's suppose that Tasha babysits and charges $5 per hour. So she makes a table here, want to know how much will she make. She's got one row for how many hours she works. So she lists that in hours, and this is going to be our X values. And then she makes another row here where we have the amount earned, and that's in dollars. And this is going to be our Y values. And the number of hours she works, she figures, what about 1 hour, 2 hours, 3 hours, or 4 hours? And so she knows that she works 1 hour, $5 an hour, she's going to get $5. Works two, she's going to get 10. $3 would be 15, and $4 would be $20, or 4 hours would be $20. The amount of money that Tasha earns is 5 times the number of hours she works. We can see that relationship here in this table. Write an equation using two different variables to show this relationship. Well, our two different variables are going to be x and y. The question is, where do they go in the equation that they wish for us to write? So we know that the amount of money that she earns, and that's in the y row here, so we'll call that y, it's an equal sign, $5, 5 times is multiplication, and the number of hours she worked, well, she's listed the number of hours here, and we're going to use x for that, so we have an x here. So we do have two variables, an x value and a y value, and we've created an equation of y equals 5 times x. Tasha can use this equation to find how much money she will earn for any number of hours that she works. Moving to the next slide here, we have example 1, using a table to write an equation. So determine a relationship between the x and the y values, and then they want us to write an equation. So in this example, we have this table, a row of x's, 1, 2, 3, and 4, and a row of y's, -2, -1, 0, and 1. So to find that relationship, the first step is to list the possible relationships that could exist between the first x and the first y values. Here, 1 and -2. Well, a couple ways we could get from 1 to -2. Well, first of all, we could add 3, or take that back. We could subtract 3, right? So 1 minus 3 is that -2. So that could be possible, subtracting 3. Another possible relationship is multiplying times -2. 1 times -2 is indeed -2, because anything times 1 is equal to itself. So let's go ahead and do step 2, determine if one relation works for the remaining values. So two possibilities, subtracting 3 or multiplying by 2. Let's see which one works. So 2 minus 3, -1. Indeed it is. 3 minus 3, 0. Checks out. 4 minus 3, is that 1? Yep, it sure is. So if we have a value of 1 and subtract 3, we get 2. 2 minus 3 is -1, 3 minus 3 is 0, and 4 minus 3 is 1. So it looks like the relationship is subtracting 3. Now we could need to go ahead and make sure that we got this right by checking out the other possible relationship of multiplying times -2. So 2 times -2, well, that would be -4, not -1. So it doesn't check out, and we could pretty much stop there. It has to hold true for everything in the table. So since that doesn't, we know that that's not the case. But nonetheless, if we check out the other ones, we see that they're not true either. So it seems to be that the first relationship works. The value of y is 3 less than x, or subtracting 3 is the same as saying 3 less than x, right? So step 3, write an equation. Y equals 3 minus x. We could translate this over to, I'm going to grab a line here to underline the pieces, the value of y, the value of y, the value of y. I need to keep going there, don't I? The value of y, and then we get blue, is, the equal sign there, is, and then the rest of it, we'll try green. 3 minus x, well, that is 3 less than x, correct? So We've taken the phrase, the value of y is 3 less than x, and we've written it as an equation. So we're good to go. Determine a relationship between the x and the y values in the relation. So here we have a couple of braces here. So we know that it's a set. We got some ordered pairs inside of that. We have 4 of them. And since they're ordered pairs, we know that our x values come first. So 1, 2, 3, and 4. Those are our x values, also known as our domain. So let's go ahead and put those in our table over here that I have on the right. We'll do 1, 2, 3, and 4 for all of our x values. And then we know that the y values come second, right? Order matters in ordered pairs, so it is the y values that come second. So our matching y values are 3, 6, 9, and 12. So we'll go ahead and fill those in. 3, 6, 9, and 12. So start thinking relationships that we could use to get from one to the other. So we could do 1 to get to 3, add 2. And another possibility would be 1, times 3. And that would also equal 3. Both of these equal 3. So we have a couple of possible rules to get from 1 to 3. One rule is to add 2. The other rule is to multiply 3. Now we need to check out the rest of them. Get my highlighter here. 2 plus 2. So if I added 2 to this, I would get 4, not 6. So I can pretty much stop there and check the next rule that I've thought of, and that is to multiply times 3. So 2 times 3, indeed that is 6. 3 times 3 is indeed 9. And 4 times 3 is 12. So it appears to be that the rule is to take whatever x is and multiply it times 3. So if we want to know what the value of y is over here, we would have to take, well, we don't want to put x3. We would be better off to do 3x. So this would be our equation that would describe the rule that we see here in the table. Looking at the next slide, we're going to talk about independent variables and dependent variables. So the input of a function is the independent variable. The output of a function is the dependent variable. Now, you've probably heard the word output before in previous lessons when we're talking about domain and x values and range and y values, those type of things, right? I've used the word input and output before. So let's look over here at the helpful hint. There are several different ways to describe the variables of a function. Well, you know about x values and y values. We've also talked about how the x values are also known as the domain. Y values are also known as the range. Also, our x values are the input, and the y values are the output. Another thing that we're going to add here that's a little bit new, well, we know our x values we could represent with just x. However, y values can be written with this f parentheses with an x inside of the parentheses. Now, there is a special way to say this, but that's going to be on the next slide. So I'm just going to call it x parentheses x, which is not the proper way to say it. But all of these things here, x value, domain, input, and x, this also matches up with the concept of independent variable. And likewise, y value, range, output, and f parentheses x matches up with the concept of dependent variable. So the value of the dependent variable depends. So this is, and I'm going to go ahead and grab this in here. The dependent variable, let's go ahead and just put a y there. We almost think of this as y, right? Dependent variable, it's interchangeable with y values. Depends on or is a function of the value of the independent variable or the x value. We could almost read this as the value of the y variable or the value of y depends on or is a function of the value of x. Now I'm going to go ahead and erase that there. I just want to highlight how those words are interchangeable there because as we move along later on, that concept is going to kind of help make things a little more clear. So for Tasha, the amount she earns depends on or is a function of the amount of time that she works. So the amount of money she makes depends upon how much time that she works. So if we kind of think of that, the amount of money that she makes depends on the amount of time that she works. So the money she makes, so if y depends on x, the amount of money she earns, y, is a function of or the amount of time she works. So the time is our x value. So in this case, we would say that X is the independent variable and Y is the dependent variable. I'm going to show you a trick how to keep that whole independent and dependent variable thing kind of squared away with which one's X and which one's Y. I'll get to that in a moment. That's what this little two white lines here, creating an X-axis and a Y-axis. Let's go ahead and put that in. As a matter of fact, this is going to be our X-axis, and this is indeed the Y-axis. So let's go ahead and look at example 2 for now. Identifying independent and dependent variables. Identify the independent and the dependent variables in each situation. Or we could say identify the X values and the Y values in each situation. Part A, in the winter, more electricity is used when the temperature goes down. Makes sense. And less is used when the temperature rises. The amount of electricity used depends on the temperature. Now, I like to use a personal strategy of circling one and then pointing to the other. Circle the one that causes the other. Or is it the other way around? Yeah, circle the one that's affected by the other. So the amount of electricity depends on the temperature. And it turns out to be whenever I do it this way, the part that's circled is going to be my dependent variable, also known as my Y value. The part that's getting the arrow pointed to it is going to be the X value, the independent variable. I think at this point is where I'm going to point out the trick of how I remember the difference between dependent and independent variable, which one's which. So let's look at this graph over here. So I've got this horizontal X-axis and a vertical Y-axis. Well, the word independent starts with I. So I could take the letter I, I think I got red there. Yep, make sure I got red. And I could just hang the letter I right there, and I'm not using a, give me just a second here, get a line. I want to make it nice and straight. I could take the letter I and hang it right there on the X-axis. And I stands for independent variable, and it hangs the top of the I. Just hook it up there, stick it right onto that X-axis, and that's how I remember the independent variable is my X values. And then maybe you're seeing this already before I do it, but then the letter D, I can just hang the side of the D right there. Let's put the curve on the D. Good. And D is for dependent. And I can hang the side of the D onto the Y-axis. So this is how I remember my independent variables. Starts with I, is my X values, and my dependent variables, they are my Y values. And if I were to start graphing this and on here, I don't know, maybe I shouldn't head down this road. But if I wanted to put this, my X values, this would be my temperature, right? TEMP. And then over here, this would be the amount of electricity. We'll just put elect for short for electricity. So if I were to graph it, if I had some kind of a graph there going up, I would realize that as the temperature increases, is that what it says? In the winter, more electricity is used when the temperature goes down. Oh, that would be the other way around. But as one increases, if I put a positive slope on it, and now I'm using a bunch of words that we haven't gotten to yet. But in this case, this would be where the temperature increases, then electricity increases as well. And I guess this would be an event of if it's getting hotter, you use more electricity. I guess you need an air conditioner instead of a heater. I think the example there is talking about seems to be that more of a heater type thing. Like when the temperature goes down, less energy used. So I'm getting totally confused in all this. So let's go ahead and move on. In item B, the cost of shipping a package is based on its weight. So the cost of shipping a package depends on its weight. It says based on, we could reword that as depends. So let's go ahead and do some circling there. One causes the other. The cost of the shipping depends on the weight. So in this case, my cost would be the Y value, hang that D on that Y axis, and my X values would be the weight. The more something weighs, as the weight increases, the price of shipping it would increase. The faster Ron walks, the quicker he gets home. The time it takes a Ron to get home depends on the speed that he walks. So the time is dependent on whatever his speed is. So in this case, dependent variable is my Y values. Independent variable would be my X values. You could almost picture it over here on my graph that the faster he walks, the faster his speed gets, right? Or actually time. It'd be actually decreases, so the amount of time. So the faster he walks, the quicker he gets home. Yeah, we'll get into graphing that stuff later on. The idea is to understand what independent and dependent variables are. The independent variable determines what the dependent variable is, or your x values determine what your y value is. Identify the independent and dependent variables in each situation. Let's just do one of them. A company charges $10 per hour to rent a jackhammer. So how much you pay is going to depend upon how much time you rent the jackhammer on. So that means that money is going to depend on the amount of time that you have it. So in this case, dollars would be the dependent variable, and the independent variable in this case would be time. Let's look at the next slide here. An algebraic expression, remember what an algebraic expression is? Think back to vocabulary there, like 5x plus 2. It's an expression, it has an operation sign, numbers, variables. That's what would make it algebraic. So an algebraic expression that defines a function is a function rule. 5 times x in the equation about Tasha's earnings, well, that is a function rule. 5 times x, or 5x, and it does have an operation in there, right? Multiplication, so 5x would be an algebraic expression. If x is the independent variable and y is the dependent variable, then function notation for y is f parentheses x. And here's where I tell you how it's pronounced properly, or how we would read f parentheses x. We actually read that as f of x, where f names the function. When an equation in two variables describes a function, you can use function notation to write it. So let's go ahead and look at the dependent variable is a function of the independent variable. So y is a function of x. Well, here a function of x, we just write that f of x. So y equals f of x. That means that y and f of x are the exact same thing. And this is very confusing for some people whenever they get into algebra, because they're used to seeing the y, but this whole f parentheses x, or this f of x thing, is a little foreign to them, not used to it. It takes a little while to get used to, but basically y can be substituted for f of x, and likewise f of x can be substituted for y, and that's what they're going to tell us in this portion right here. Since y equals f of x, Tasha's earnings, y equals 5x, can be rewritten in function notation by substituting the f of x for the value of y. And right here we have that, f of x equals 5x. So y equals 5x is exactly the same thing of f of x equals 5x, because as I said, y and f of x are actually equal to one another. We've proven that here in this demonstration here. Sometimes functions are written using y, and sometimes functions are written using f of x. I like my functions written in y. That whole f of x thing, I understand it, but I prefer y personally. Looking at the next slide, example 3, writing functions. And I'm looking over here. Do I want to go to this first? Yeah, why not? You can think of a function as an input-output machine. It's a function machine. For Tasha's earnings, f of x, also known as y, equals 5x. If you input a value of x, the output is 5x. So whatever we take and throw into the machine, in this case, the function of the machine is to take whatever goes in and multiply it times 5, or 5 times whatever, or put the 5 in there. Or to be more precise, what this machine's saying is whatever goes in the machine, you need to multiply it times 5. Take whatever x is, substitute it, and then multiply it times 5. So if we put in and let's leave the x for a moment, we'll put that to the side. If we put in a 6, substitute 6 for x, 6 times 5 is 30. That's why the 6 is blue and the 30 is blue. What if we plug in a 2? 2 times 5 is 10. So we would get a 10 back. Notice that the 2 is green and the 10 is green. Well, we can even put variables in the machine. Put an x in there. 5 times x, well, that is 5x. It takes whatever you plug into the machine, Substitute it for x, multiply it times 5, and it comes out the other side of the machine. This is known as a function machine. Very, very common illustration for teaching the concept of what a function is. So writing functions, here in example 3, identify the independent and dependent variables, write an equation in function notation for each situation. Remember, function notation is just that fancy f of x instead of y thing. A lawyer's fee is $200 per hour for her services. The fee for the lawyer depends on how many hours she works. So again, I like the whole circling thing. The fee depends on the number of hours. So independent variable, y is fee. Dependent variable, x is hours. So we're going to let h represent the number of hours the lawyer works. So the function for the lawyer's fee is f of x is equal to 200x. Remember, we could go ahead and substitute y there. We could just say y equals y, the dependent, or let's go ahead and say it this way. Y, the fee, is equal to 200 times x, the hours, right? This is our x value here. But all we did is we just substituted the y with function notation there. And instead of y equals 200h, we get f of h because h is what's getting plugged in, right? This is saying that take whatever h is, plug it in, and that would tell you the function of it. Identify the same directions, so for B here. So the admission fee to a local carnival is $8, so it costs you $8 just to get in. Each ride costs $1.50. The total cost depends on the number of rides ridden plus the $8. Now that's a little tricky because this is what later on we're going to call y-intercept. This is the starting amount, but we're not quite there yet, but we're kind of starting to introduce that type stuff. So the total cost depends on the number of hours. So what depends on what? So total cost, we're going to go ahead and circle the total cost. That depends on the number of rides that you ride. So total cost is your y value. Hang that d on the y-axis and hang the I on the x-axis. So x is going to represent the number of rides. We're going to let r represent the number of rides that's ridden. And therefore the function for the total cost of the carnival is the function of r, the function of the number of rides that we ride, is equal to 1.5 times r. R is the number of rides, so $1.50 per ride plus the $8 it costs to get in. So it's a little bit of a preview of later on whenever we get into linear functions, and this is going to be what's known as y equals mx plus b, but that's a little ways down the road. So identify the independent dependent variables, write an equation in function notation in each situation. Stephen buys lettuce that costs $1.69 a pound. So the amount of money that Stephen spends is going to depend on how many pounds that he buys. So in this case, and I need to change my color there, in this case, the amount of money is going to depend on the number of pounds, LBS. So in this case, this is our y value, our dependent variable, and this is our x value, our independent variable. I really do. I picture the d hanging on the y and the I hanging on the x in this case. So let's go ahead and create an equation for us. It is a function of pounds, determines how much money that he gets, and it is $1.69 a pound. So in this case, the function of, and what's causing it? Let's look at the example over here. It's the number of rides, so our x value needs to go in here. It's the number of pounds. So let's just do p for pounds. There we go. So f of p is equal to $1.69 per pound. So we would have f of p is equal to 1.69 per pound. Now, I also like to think of this. Sometimes I'll use the circle method, but honestly, sometimes I sit and think what causes one causes the other. So in this case, uh, what causes what in the Stephen buys lettuce that costs $1.69 a pound? What's the total amount of money that he spends, right? Well, what causes that? Well, it all depends upon how many pounds that he gets. So it is the independent variable that affects the dependent variable. The dependent variable all depends upon what the independent variable is. That's the whole idea behind it. It depends, right? How much money are you going to spend? I don't know. It depends. Depends on what? Well, it depends upon how many pounds I get. The dependent variable, I like to think of this as dependent. You can do whatever you want. You can buy it however many pounds you want. You can ride as many rides as you want, or you can. Well, I guess sometimes lawyers do charge us however many hours they want. It's the dependent variable, nonetheless, or yeah, the independent variable. Sorry, independent, do whatever you want, but one causes the other. So often, I might also think of it, what causes it? Well, the hours causes the fee, so hours is my x value, or the number of rides affects the total cost. The total cost is caused by, all right? Or you can go the other way. This depends on that. Totally up to you, whichever way you want to go. Looking at the next slide here, evaluating functions. Well, if we evaluate something, we know that whenever we evaluate it, we substitute a value in, and we go ahead and uh, break it all the way down to just one given value. That's what evaluating is. We've had that in our vocabulary before. Reading math over here, functions can be named with any letter. F, G, and H are the most common. You read F parentheses 6 as F of 6 and G parentheses 2 as G of 2. So it doesn't necessarily have to be an F. And this will really start getting confusing because teachers will introduce to students that it's F of X, and then they'll see something that says G of T or H of X. Still, it's the same thing. We can always think of this as a Y value. Just like we can substitute F of X with Y, we can substitute G of T with Y as well and think of it as Y equals 5X or Y equals 2.30T plus 10. Either way, if you want to think of it as Y instead, that'll work fine. But the point is that G of T is just the same thing as F of X. So for F of X equals 5X, find F of X when X equals 6 and when X equals 7.5. Now, this might really sound confusing, but if I said y equals 5x, find the value of y when x equals 6 and when x equals 7.5, you'd be like, oh, I know how to do that. Now, all of a sudden, this f of x thing starts to sound a little more confusing. So if you want, again, just think of it as y. So f of x equals 5x. So we're just going to substitute in the value of 6. There we go. Multiply it, we get 30. So f of x is equal to 5 times 6. Just substitute whatever is in the parentheses here, gets substituted into the algebraic expression, and then we evaluate it. That means get it all the way down to one number. F of x equals 5x. Well, what does f of 7.5? Well, substitute in 7.5 for the x, and it's 37.5. For g of t equals, and here's the expression, we're just going to substitute in g of t is equal to 2.30t plus 10. So what is g of t? Well, substitute in t, do the math, we get to 14.6. If you want, you can pause it, take a look at each of these and check the math if you want to. But nonetheless, basically, it's all the same thing. We're just substituting it in. For h of x equals 1 half x minus 3, find the h of x when x equals 12 or when x equals negative 8. So h of x equals 1 half x minus 3. So what is h of 12? Well, substitute 12 in for the x. Do the math. 1 half of 12 is 6. 6 minus 3 is 3. Example 5, finding reasonable domain and range of a function. Over here, we have a little bit of text here to tell us about something, and that is when a function describes a real-world situation, every real number is not always reasonable for the domain and range. For example, a number representing the length of an object cannot be negative, right? You can't have a negative 5 feet. And only whole numbers can represent the number of people. How many people were at the show? Oh, there were 23.6. You can't have 6/10 of a person. There are either 23 people there or 24 people there, but the numbers have to make sense for real world problems. So Manuel has already sold $20 worth of tickets to the school play. He has 4 tickets left to sell at $2.50 per ticket. Write a function to describe how much money Manuel can collect from selling tickets. Find the reasonable domain and range for the function. So we have the money collected from ticket sales. That is the function of x. It's the y value, right? The total amount of money he makes. We would say that would be the y value, but we're just substituting it with f of x. So the money that he makes from ticket sales is $2.50 per ticket plus the $20 already sold. Let's go ahead and translate this. Is equal sign. $2.50, bring that down. Per means to multiply, get our multiply sign. For every ticket we sell, we're going to represent with the value of X plus as addition. The 20 already sold, we'll represent that as 20. If he sells X more tickets, he will have collected f of x equals 250x plus 20. We can see that right there, 250x plus 20. And f of x is just like y. Manuel has only 4 tickets left to sell, so he could sell 0, 1, 2, 3, or 4 tickets. All reasonable domains are 0, 1, 2, 3, and 4. That's a reasonable one. He can't sell 5 tickets because he doesn't have 5 tickets. He's only got 4 more. And he can't sell negative 20 tickets because, well, that wouldn't make sense either. So our domain, 0, 1, 2, 3, 4. Substitute these values into the function rule and find the value or find the range values. So our x values are 0, 1, 2, 3, and 4. Substitute it in. We can see what's substituted in each time here. After you do the math, you come up with 20, 2250, 25, 2750, and 30. So the reasonable range for this situation is $20, 2250, 25, 2750, and 30. Now we could write these as ordered pairs right here. I want to go ahead and point this out. We could write each one of these as ordered pairs. Whenever x is 0, what is the value of y or f of x? The f of x value is 20. Another one would be whenever x is 1, what do we get? We get 2250. And I guess since it's money, I'll throw the 0 on there. Whenever x is 2, what is it? It's, what, $25, right? And so forth. 3, 2, 2750, and 4 would go with 30. That should bring us to our guided practice. Apply the vocabulary from this lesson to answer each question. The output of a function is the blank variable. Well, the output is our y values, right? So let's go ahead and picture that. I think I'm on white or red. There we go, white. Picture that good old graph there. And the y values, the output, right? Output. And I am in red. Let me go back to white. The output is also known as our y values, which is here. And what is it that can hang on there? It's the d that can hang on the y-axis. So we know that it is indeed the dependent variable that is the output of a function. In an algebraic expression that defines a function is function rule or function notation. It is the function rule. Function notation is that whole f of x thing, right? That is also equal to y, right? But the f of x portion is known as function notation. The function rule is actually remember when I had the f of x equals 5x? This is the function rule over here. The actual algebraic expression that is set equal to the f of x. Determine a relationship between the x and y values, write an equation. Well, to get from 1 to negative 1, right? To get from here to there, what could we do? We could add, or we could subtract 2. So 2 minus 2 is 0, 3 minus 2 is 1, 4 minus 2. So it seems to be that we're subtracting 2 each time. So we could say here that y is equal to, take our x value and subtract 2 from it, right? We could also say that f of x is equal to x minus 2. See, all I did was I just substituted f of x for y. It's really, it seems intimidating at first, but really, just realize you can change them out. Let me see, 1 to 4, what if we did plus 3? Does this hold true? Plus 3? 2 plus 3 is 5, so it's not plus 3. Let's see. It's not plus 3. Is it times 4? Nope, it's not times 4. Now, let me pause for a moment. Think about this one. And I just figured it out. It is multiply times 3 and then add 1. 1 plus 3, or 1 times 3 is 3, plus 1 is 4. 2 times 3 is 6, plus 1 is 7. 3 times 3 plus is 9, plus 1 is 10. 4 times 3 is 12, plus 1. So it says take whatever our x value is, multiply that times 3, and then let's add 1 to it. So we could say that the y values are equal to 3 times x plus 1. So, or better yet, the f of x is equal to 3x plus 1. I had to pause for a little bit. It took me a little bit to figure that one out. But identify independent and dependent variables in each situation. Remember, one causes the other. The independent variable causes the dependent variable. A small bottle of water cost $1.99 and a large bottle of water cost $3.49. So it appears to be that the dollar amount is dependent on the size, or that is to say that the size determines the cost. An employee receives 2 vacation days for every month worked. So let's go with 2 vacation days for every day worked. The number of days depends on the months worked. So in this case, days is the y value, months worked is the x. So let me think of this. Does the number of months you work determine the number of days vacation that you have? Indeed, it does. So the independent variable, hang that I on the x-axis, the independent variable is the number of months worked, and the dependent variable is the number of days vacation time that you have. Example 3, identify independent dependent variables, write an equation in function notation for each situation. So now function notation, it's just using f of x instead of y. An air conditioner technician charges $7 or $75. I wish it was $7.50. $75 per hour. So in this case, let's think our way through it. The amount of time, number of hours, determines the, so it's the number of dollars. There we go. I almost get my arrows backwards. I do kind of switch back and forth from things. So the money depends on the amount of time. So the amount of money is the y value. The hours is the x values. So y is equal to number of hours times $75, right? So the total cost would be equal to 75 times x, which is the number of hours worked. So we could say the f of x is equal to 75x. Evaluate each function for the given input values. So we have number 9 there. They say if f of x, the f of x is equal to 7x plus 2. They want us to find the f of x. So what is the f of x whenever x equals 0? And what about the f of x, not 0, go back, the f of x whenever x equals 1. And to be more precise, it would probably be better to put that as an arrow instead of equals there, whenever x is 0. So let's go ahead and substitute that in. So the f of, and to be exact, I should do this, f of 0 equals 7 times 0 plus 2. So in this case, we would have the f of 0 equals 0 plus 2. And so f of 0 equals 2. That would be the answer here, which also is the same as y equals 2, right? And what about if we go ahead and do the f of 1 equals, and then the rule, 7x plus 2. So we would have the f of 1 would be equal to 7. Just substitute 1 in for x. So f of 1 is equal to 1 times 7, 7. So the f of 1 equals 9. All right. And I think I'm going to leave the construction company question alone. So that completes all of my instruction for the Algebra 1 textbook lesson 4-3, writing functions. Now go level up your learning.